All right, now the next speaker is Claudio Lazarte from the University of Valencia, and he's going to talk about stability analysis of l-Proca stars.
Good afternoon, everyone. It's a pleasure to be here. I'm Claudio Lazarte, a Peruvian PhD student from the University of Valencia. And this is my first talk in Brazil, so I'm very happy and very glad to be here. Today I'm going to show some of my results of the study of a stability analysis of l-Proca stars, a work that I performed under the supervision of Nicolás Sánchez Gual, José Antonio Fona, and Miguel Alcubierre. And to, well, okay. Okay, and just to make a quick introduction, let me mention some basic definitions, some basic ideas. The Procestar are stationary classical solutions for cell gravitating configurations. These objects are made of massive complex vector bosonic fields, which you know that they are called Proca fields. And since these fields have a bosonic nature, all of these objects are classified as bosonic stars. Oh, sorry. There are many motivations to study these objects. I will put just two here. From the cosmological point of view, this object could be made of dark photons produced in the early universe that could be a significant component of dark matter. And also from the astrophysical point of view, we could say that these Proca stars could be black hole mimickers. For example, there is a study in 2021 when the gravitational wave signal 190521 was interpreted as a merger of Proca stars. But in this case, in this work, I also want to quote an additional motivation. I will introduce a generalization of a multi-field Proca star, and for that, I could take this idea about a quantum physics motivation of multi-field Proca stars that we can take from this work that was done in 2023 for Miguel Alcubierre, Juan Carlos Degollado, Darío Núñez, the researcher from Mexico, where they found that a gravitating distribution of excitations of a single quantum zero spin field source the same space-time of a multi-field boson star in the classical regimes. So if we consider the quantum nature of these bosonic fields, it's interesting also to take into account that they, in the regimes, in the classical regimes, they should behave as a multi-field bosonic stars. Okay, let me introduce the action for this system. Basically, what we have here is the Einstein gravity and complex Proca fields couple minimally coupled with the Einstein gravity. All of them have the same bosonic mass, and we are going to focus just in the spherical symmetric equilibrium configurations. In 2016 was presented the first ansatz for the zero Proca star or the single field Proca star. Uh, and the work that we did with Miguel Alcubierre was generalize these ansatz for the case when the Proca star is a star with a multi-field content, but preserve the spherically symmetric of the space-time. For this purpose, we have to choose a specific number of fields that form the star. This number is given by 2L plus 1, where L is the angular momentum number of the spherical harmonics. And as we can see, these ansatz have the harmonic time that all bosonic stars have, but also have the scalar potential and the vector potential. But in this case, the scalar potential and the vector potential have angular dependency given by these spherical harmonics. Additionally, we had to introduce also angular components for the three-vector potential with, well, we cannot see here, but here there are angular derivatives of the spherical harmonics. And in this way, this system is not also sourcing a spherical symmetric space-time. It's also fulfilling the Gauss constraint that these kind of fields have to fulfill. Okay, so as we already know the angular dependency of these fields, what we have to do is solve the system of equations for the radial dependency. We can see here some of the radial dependency for the matter variables and the metric variables. We obtain these solutions solving the system of these equations using spectral methods. And well, all of them looks very well. They decay rapidly for large R as we expected for massive fields. The spacetime is regular everywhere. And also we can infer some ideas about the morphology of these stars watching the behavior of this energy density. For example, for the case L equal to 0 and L equal to 1, we have spherical Proca stars. And for the case of L equal to 2 and 3, for example, we will have spherical shells. But the most interesting thing that we obtain from this analysis comes from the fact that the case for L equal to 1 has to be ruled out. The reason is because we have here this function A that represents the radial component of the three-vector potential and is different of 0 in the origin, which means that in the origin we will have a vector that also have angular dependence and will be a multi-value vector function at the origin. That means that in that point we lack the regularity of the system. But this lack of regularity is in the matter fields, it's not in the space-time. So we cannot avoid changing the coordinates. So, well, all of that compels us to rule out this solution. If we want to analyze these equilibrium solutions from the point of view of time evolutions, we have to begin from the value L equal to 2, as we did. Okay, let's talk about the stability analysis. In order to determine the astrophysical viability of these systems, it's important and necessary to assess their dynamic stability and propose also mechanisms of formation in the universe. Previous stability analysis showed that the zero Proca stars, which mean the single field Proca star, are stable under radial perturbations in 1D simulations. But the story changed if we consider 3D simulations, because in that case, they are unstable and lose the spherical symmetry, migrating to prolate configurations. That is the reason why in this study, if we are proposing a generalization of the spherical Proca star to a multi-field Proca star, and if the single field Proca star are unstable in 3D simulations, we decide to go directly to perform 3D simulations to assess the stability of our system. Okay, I use the 3+1 decomposition. This is something standard. We will have here the potentials and the electric and the magnetic field. I will skip this. And as I mentioned before, the L equal 1 case is unavailable in this case, in this contest. So we begin our studying of non-trivial values of L involving two Proca stars, which means L equal to Proca stars. For that was needed 80 dynamical variables. The reason behind that was that for two Proca stars we have 5 complex Proca fields, which means 10 real vector fields, Proca fields. And due to the 3+1 decomposition, we have to multiply that for 8, include a damping variable to stabilize the evolution as well. So at the end, to evolve this system, we need to evolve 80 dynamical variables. For example, for the case of two Proca stars, we could see here the angular morphology or dependency for the case of m equal to 0, m equal to 1 and minus 1, m equal to 2 and minus 2. This plot shows the parameter space for the 3 different values of L. We are focusing just in the case of L equal to 2. And we perform the evolutions using the Einstein toolkit in 3D dimensions. For example, for solutions, the more compact solutions that are in the left part the left part of this parameter space, we found that they are unstable and collapse to black hole. That was something that we were expecting, sorry. More interesting solutions were, for example, for the solution at the right of the maximum total mass of the configurations, and also for less compact solutions. Both are also unstable, but not collapse to black holes, migrate to a new configurations. And today I will focus just in this kind of in the solutions that are close to the maximum mass configurations. I mean the B solutions. I will show some snapshots, some movies for that. So let's see. This is some 2D views for the scalar potentials with different values of m that conform the two Proca stars, and also where they are superposed coupled gravitationally, they form the spherical morphology with a shell, the spherical shell that we mentioned before for the energy density. And let's evolve these systems. Well, now we can see how they evolve. And something interesting what happened fast and quick is the migration of the spherical symmetry to another symmetry, right? Well, the movie is repeating. Another thing that we can see also is, for example, for the case m equal to 0, we can see, not clearly, but in some snapshot, we can see dipole forms. For example, in this one, for t more or less on 5,000, this is a dipole with some additional structure around it. For here, for example, that previously we have this structure. We now have this structure. That means that now we have also a dipole. But something that doesn't change is this structure. This is also a dipole. This is the plane xy for the field with m equal 2. And in all the evolution, hold the same morphology. Okay, so let's try to interpret these results. In the previous studies with single field Proca stars, what people found was that for the case of m equal to 0, L equal to 0 Proca star migrates to the case of L equal to 1, the dipole Proca star. They also performed some simulation using the case m equal to 0, L equal to 2, and migrates to the case of m equal to 0 to L equal to 1, which means that no matter which value of L you have, they will migrate to the case of L equal to 1. In our simulation, we found the same for these components of the two Proca star, but also we found that the case of m equal to 1 with L equal to 2 migrates, preserving the same value of m, but changing from L equal to 2 to L equal to 1. And the same for the case of m minus 1. But these spinning Proca fields with L equal to 2 and m equal to 2 seems to preserve their morphology. So what we could have in this case, well, we cannot see here what I wrote, but I will try to say that this could be a multi-L Proca star formed by the superposition of these three fields that could be forming one Proca star in axial symmetry plus two spinning Proca stars that previous studies showed as well that they are unstable. So I think this result deserves more studies. Now we are checking if this system converge at large time, because we obtained using performing some convergent tests that they converge good with 4 order at a certain time. We are trying to solve the problem of convergence at large time. So now we cannot be completely sure if these systems are stable due to the numerical errors or is a physical stabilization coming from the other fields. So till the moment, this is a preliminary result. Okay, for the time I will skip this. But just to mention quickly, we solved the problem of m equal to 4 that were appearing in our simulation, extending the grid, putting an outer refinement level. So if you have questions about this, we can talk more about it. And just to conclude and summarize all this talk, we enlarge the solution space of Proca stars, including multi-field solutions with a richer inner multipolar structure. We also found, performing numerical simulations in 3D without imposing any symmetry, that l-Proca stars are unstable under non-spherical perturbations and lose their spherical morphology. And we also observe this migration from L equal to 2 and L equal to 1 in our configurations, except in the fields that have m equal to 2, m equal to 2. And this result deserves more analysis to see if actually we have a multi-L Proca star or the spinning Proca stars that are also in the system will migrate to L equal 1 configurations, or they are stabilized by the other fields. So that's it. Thank you very much.
Thank you, Claudio. We have time for a really short question.
Thank you very much for the talk. In the case L equals 1, in the beginning you said you had some issues because your field can be multi-valued at the origin, right?
Sorry.
When you had the stars with L equals 1, one of your fields was multi-valued at the origin, so this told you that you had to disregard this case.
Yes.
But at the end you have multi-L with L equals 1, so do you have any problem with that?
There is a the thing is that in our equilibrium configurations, when we have L equal 1, we are imposing a spherical symmetry. And due to the spherical symmetry, the solution with N equal to 1 have to be ruled out. But in the dynamical evolution, seems that dynamically the L equal 1 could be formed, but in this case, the system has not a spherical symmetry anymore. So I think theoretically we can see that if this one Proca star exists, this is not for a spherical symmetry spacetime.